Today we discuss about hinge reaction. Actually, hinge reaction can be because of three different reasons. One is rotation. That means when an object is rotating, it will cause some reaction. Okay. Second one is uh, at rest or static. Suppose if a body is not rotating, doesn't mean hinge reaction won't be there. It will be there sometimes. Okay. Last thing is because of acceleration. Acceleration or torque. Okay. These three things are there you need to understand. Sir, I'm not getting it. Let us do one thing. Let us study one after other independently. And sometimes what happens, some questions will be there where more than one will be involved. Then no need to worry about it. Take one at a time and find the value. That means hinge reaction due to rotation, you just find it. Okay. And hinge reaction due to static condition or acceleration torque, whatever it is, and superimpose them. With ease you can do. So when we go for the first part, let us make sure those remaining two are absent. How to make it? Observe carefully. When I take a rod like this, when I take a rod, okay, and right, simply I'm going to hinge it here in a vertical plane. That means G is there like this. There is no rotation, there is no angular acceleration, but still this hinge will apply some force, no? Otherwise, how it will be at rest? It will be moving, right? So the hinge reaction will be equal to mg. Easy to find, but uh, this is only static condition, right? So what is my recommendation is that, okay, let us eliminate this part. How to eliminate? Keep this rod on a horizontal table. Once you keep the rod on a horizontal table, then G won't be there. Now, rod is there and acceleration torque. That means I'm not applying any force or any torque. It is not accelerating, it is at rest. Because it is at rest, rotation is also not there. So rotation is not there. Static condition doesn't need to hinge to be to provide reaction and acceleration. All three are not there. Hinge reaction is zero. Done. Now let us start with the first one, rotation. Right. If you start rotating it in a horizontal plane like this with omega, will this hinge provide reaction or not? It must provide reaction, right or wrong? Otherwise, how it can rotate? Okay. So first thing is that hinge reaction due to rotation or angular velocity. I think you know this one. This is nothing but what, tell me? Centripetal force. Okay. So, sir, then how to deal with it? Actually speaking, you can take it by integration. Take a small segment dm. This dm need some force towards center. That is nothing but centripetal force. Okay. M dm r omega square or x omega square, you take it. And then, sir, I'll add the forces, integrate. Definitely you can do integration. But my recommendation is just remember this. In case of rotation, crush the body, keep at the center, and calculate centripetal force over. So just remember this in case of rotation. Right? Okay, in case of rotation, what would you tell me? Simply calculate centripetal force. While calculating centripetal force, in rotational mechanics, we won't get particles. In rotational mechanics, we won't get particles, na? Always bodies will come. We, if you are lucky, you will get one question, that's it. So always body will come. In case of body, what to do? You can use what? Use center of mass. That means why I'm giving you this statement is I clearly told you don't use center of mass in case of rotation because it gives you wrong answers. The reason is that Suppose if you want moment of inertia, sir, I want moment of inertia of rod. I'll crush the rod, keep at the center. Job done, right? That's what you may feel. But that's not allowed, na? Because moment of inertia of a rod is ml square by 3 in this case, right? So remember, in rotation mechanics, crushing and keeping at the center is not allowed. And there are some exceptions. Whenever exception is there, I'll clearly inform you. While calculating centripetal force, definitely you can use the while calculating centripetal force, you can crush the body and keep it the center. In this case, answer will be if the length of the rod is L, mass is M. The hinge reaction will be centripetal force only, mr omega square. M, what is R? L by 2 omega square. Why R is L by 2? Why R is L by 2? Because the distance between center of mass to the hinge, it will be L by 2. Okay. One more small doubt. Now, direction of hinge reaction. Two directions are there. I'll give it to you. Someone has respond. The first direction is this is direction 1, this is direction 2. Which direction is correct? Hinge reaction on the rod. Remember, centripetal force will be perpendicular. Remember, centripetal force will be towards center, right? That is on the body. On the body, if you are asking, yeah, correct. It is towards center only. So answer is 1. Clear? This is the first thing you need to learn. Once you understand this, question number 1 and 2 with ease you can do. I can't give too much of time there. Look into the question, pen and paper. You can give answer in one step. First question, answer, tell me. Question number 1, easy, straightforward. Okay. There is a particle. Particle means much more easy actually. Bodies are little difficult. Particles are very easy. So in this case, hinge reaction is rotating, right? So when it is rotating, hinge reaction will be, we give the symbol R to hinge reaction. R is equal to mr omega square. In this case, ml omega square. That's it. Because particle, na? And hinge reaction will be like this. You know that as always, centripetal force is towards center, na? That's why I'm going to keep it here. This is the hinge reaction R. Understood? Go ahead with the question number 2. Next one. We have a rod and it is rotating about the hinge. In this case, I told you already, it's centripetal force. It's always what, tell me? Crush the body, keep it the center, find the value. So hinge reaction R is equal to what? M. L is L omega square. Is it right or wrong? Absolutely wrong. Because when you're crushing and keeping it the center, the distance becomes what? Tell me? L by 2. So M L by 2 omega square. Clear? M L by 2 omega square. Direction again. You crushed it, keep it center, right? Force will be towards center, right? So you have to indicate like this. This is the direction of hinge reaction. R. That's it. We don't discuss much. This is easy. This becomes complex when there is a question where 2, 3 are involved. Okay. So first part is over. Rotation. When body is rotating, rotation alone, if you take it, crush the body, keep it the center, there will be a reaction towards the force towards center is nothing but centripetal force, mr omega square. That's it. Okay. Good. Now static condition. That means when the body is at rest, then also hinge reaction is possible. Right? Go ahead with the question number 3. With ease, you can solve question number 3. Sir, how to calculate? Static condition already we discussed. Use the conditions to get the answer. Okay? Right. Go ahead with the question number 3. Question number 3. There is a rod which is hanged like this and find the hinge reaction. This is the question, right? Good. You can deal with this. So I'll tell you a small technique here. Although you don't need it here, directly you know, sir, actually gravity is pulling down like this. Definitely hinge reaction will be upwards and the body is not rotating, not translating, nothing is there. So hinge reaction is equal to mg. Absolutely right. Good. But let us go for little detail discussion here. Now, to get the hinge reaction, what we say is that no need to worry. Don't decide this will be the hinge reaction. always go through free body diagram. Force free body diagram, torque free body diagram. Okay, because the body is at rest and it's not accelerating, equilibrium condition. So net torque will be zero, net force is zero. Use it, you will get the answer. In this case, what we do, we write the free body diagram, downward mg and hinge reaction. Check it R1, R2. This is the point you need to know. Since we don't know exactly what are the direction of hinge reaction, what is the magnitude of hinge reaction, when you don't know something, we will take that force as combination of two mutually perpendicular forces. I briefed about it previous segment. Okay, take it for granted, these two. Okay, right. Similarly, you can go for force free body diagram also. I'm going to write the force free body diagram. This is R2. This is R1. And last one is downward mg. Downward mg. By looking into this immediately, if you have enough practice, you will say, sir, R2 must be zero because there is no there is no counter balancing force because net must be always zero. It's equilibrium condition, right? So net must be always zero. There is no force to balance R2. So what's the conclusion? Tell me. R2 must be equal to zero and R1 must be equal to mg. Net force equal to zero. You don't need to go for torque also. Torque is also not required. Simply you can say hinge reaction R1 is equal to mg, R2 equal to 0. This is easy. It is not necessary always all problems can be solved with ease by using only force free body diagram. Sometimes you need to do torque free body diagram also. Go ahead with the question number 4. Now there is a door and is at rest. It's static condition, right? It's at rest. It's easy to deal with. Net force equal to 0, net torque equal to 0. But only thing is that here two hinges are there. One hinge means no problem, a less problem I can say. And two hinge means always there is a problem because two hinge reactions, sorry, each hinge will give you two mutually perpendicular, isn't it? No problem, we'll solve. What we do is that we take first center of mass and mg will act there, right or wrong? Mg will act and mass is given directly. Shall we take the number? What is the mass given? Tell me. 200 kg. So mg is what? Directly I'll write 2000. Okay, good. Next, first hinge. Whenever there is a hinge, you have to take hinge reaction as combination of two mutually perpendicular forces. Okay, like this. So this is a hinge reaction. Understood? Vertically upwards. Yeah, good. This is a hinge reaction. This is R1. This is R2. And again, this is R3. This is R4. Sir, how do you know hinge reaction will be in that direction only? Then we don't know. I don't know. Just I'm expecting that if I'm wrong, don't worry. Equation will take care. Okay. So small concept I would like to give. Most times I'll say like this. If you don't know direction, don't worry. Equation will take care. Okay. Sir, is really equation takes care? And you need to understand in a problem, okay, if you know direction of all other forces except one, then only it can take care. If you have 5 forces and you don't know direction of any force, then it's a problem. Okay. Okay. Right. It's okay. Continue. What to do? We have to do what? Force free body diagram also. No? So I'm going to write the force free body diagram here. I'm going to copy these forces and right. Anyone is there who can give conclusion by looking into the free body diagram? This free body diagram you looked at. Look into this free body diagram. What you can conclude? There are some conclusions you can give.
Sir, R1 upward, R2.
Very good observations. You know, if you observe these things, R R1 plus R3. R1 plus R3 is equal to 2000. Okay, right? And one more thing, there it's clearly given that load is equally good. When load is equally good, then you can simply say that R1 equal to R3 equal to 1000. You can take that's okay, fine. The next part is that R4 plus R2. Okay, R2 plus R4 equal to 0. That implies R2 is equal to minus R4. What does that means? That is, you took the direction wrong. One must be the other way around. That's what it is saying. It's okay, fine, but bad luck. Beyond this, we can't do anything with the what? Free body diagram of the force. Now, what to do? Force free body diagram is not given the result. Tell me what to do. Tell me. Force free body diagram is not giving the complete result. What to do?
For torque is given, the torque is
Very
equal
simple.
to 0.
Definitely. Now we have to take the axis, right? Is it the system is at rest or accelerating?
Yes.
At rest. At rest means where should we take the axis? Tell me, where should we take the axis? You have to give answers.
The hinges.
No. Actually speaking, okay, hinge is correct. Actually speaking, you can take axis anywhere. But Tarun, tell me, why should we take at the hinge?
Because the door is rotating on the
Not
hinge.
exactly, it is not rotating. Why we are taking at the hinge is very
So
simple.
because we can
Tell me.
minimize the number of forces,
Very
R3
good.
and R4,
Very good.
no
Very
need to
good.
consider.
Yeah. So by taking axis at the hinge, we are eliminating that one. So observe, by taking axis here, you just eliminated R4, R3, R1 also, because the line of action is along the axis now. So concentrate here right now in terms of torque. Although you see that 1, 2, 3, 4, 5 different forces are there, but in reality these three are killed. They're not there. Only R2 is there, and gravity is by default we have. So with ease we can solve. Now go ahead with that. About that axis, net torque equal to 0. Okay, this is clockwise, right? Clockwise torque. Let us take clockwise positive. Yeah, you can take anything. Clockwise positive, anti-clockwise negative. Or by default, we take anti-clockwise positive, right? So let us follow the rule, anti-clockwise positive. So this torque, about this axis, the torque will be force into perpendicular distance. What is force? Force is 2000. Okay. What is the perpendicular distance? Length is 1 meter. So perpendicular distance will be 1 by 2. Right? 2000 into 1 by 2. And that is clockwise. So minus sign. Then R2. Oh, wait. R2 also clockwise only. So minus sign. R2 into perpendicular distance. One among my student has to give. I won't tell. What is the perpendicular distance? Tell me. Tarun.
Yeah.
How much?
3.
Not able to. Someone tell me what the perpendicular distance? This distance.
3 meters.
Very good. 3 meters equal to 0. Okay. So if you solve this, you will get the answer. R2 is equal to minus 1000 by 3, right? Minus 1000 by 3 Newton. 1000 by 3 Newton. Yes or no? Check it. Right. Why minus sign? That means mathematics is speaking with you. No, 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 no. R2 direction is wrong. R2 must be like this. Okay. That's it. We got R2. Then R4 is with ease, right? R4 is equal to minus of R2. So it will be 1000 by 3. That means R2. So R4 direction is good, but R3 direction is wrong. How I solved it? Tell me. I solved by using torque equation. Net torque is equal to 0. Net force equal to 0. We solved it here, right? Check it. This is net force equal to 0. That's sufficient for us. Torque is not required. Here, torque is required. So the second part of hinge reaction is very, very easy. Second part of hinge reaction is very easy. How to deal with it? Very simple. Okay. Use Net force 0, net torque is 0 when it is in rest, when it is at rest. Now, question number 5. Now we go to the third part. That means, concentrate here. In this segment, omega 0, that means there is no rotation. No rotation means no angular velocity. There is no angular velocity. So centripetal, I'm going to eliminate the centripetal, okay? And body is not at rest. So net torque is equal to 0, won't be there. There is some torque. Alpha is equal to, not equal to 0. Some angular acceleration is there. In this case, what to do? Okay. In this case, what to do? The last part. Okay. Okay. I'm going to explain this by taking a problem. There is a rod like this. There is a rod. Okay. And we take axis here. Obviously, it is hinged at the one end and it is in horizontal position. That does means what? Gravity will act like this, G. Yes or no? Gravity will be there. And someone is holding this one. Something like a scale or something you can do. One end is hinged, it can rotate freely. Other end is just held, you held it. And when you release it, what happens? The scale starts rotating like this. And scale or rod, whatever you want to take it. Now, it comes down like this, right? Good. While it is rotating, the hinge will give you hinge reaction. Sir, I don't know hinge reaction. Don't worry, it's your choice. You can take any two mutually perpendicular. You take it as R1, R2. Okay. And of course, gravity also will be there. Downward at what, tell me? Mg. Mg is the force, right? First of all, write down the free body diagram. Same method. Instead of using tau 0, tau is equal to I alpha. That's it. Over. Sir, that does means hinge reaction is not a separate segment. It's Newton's laws only. Newton's laws in rotation only. You are right. But understanding like this will give you complete clarity. When complex questions comes, you can do it. Remember, complex questions can be handled by dividing them into pieces. Straight away, if you look into it, it may be complex. Okay. So I think you got my point. Same how we did in case of static condition or equilibrium condition and dynamic condition. Same thing we do. Nothing. No difference. Let us continue. Now, tau is equal to I alpha. Right. I take the axis here. Sir, by taking axis here, don't you think you are killing the R1, R2? Yes. But we need to find R1, R2 now. Don't worry, we'll try. First and foremost thing is here, right? That is mg into L by 2, that is torque, is equal to I alpha. I is ml square by 3. I hope that you know why 3. Okay. Parallaxes theorem. And mm gets cancelled. We got alpha. Alpha is equal to 3g by 2l. Good? Got it? Fine. There's the first part. Then sir, wait a minute. We can write force free body diagram also. 100% we can write. This is valid. Always it is valid. It's not like, rotation case of force free body diagram. Definitely it will work. Okay. Now, if you look into that, sir, why you are solving it? R1 equal to mg, R2 equal to 0. Isn't it? No. If you are doing that, that means you got biased with what? Static condition. R1 equal to mg only when it is at rest. It is not rest, it is accelerating. Right now it is being released. Once it release, it is accelerating. Yes sir, no. Not allowed. Okay. Right. Okay, sir. Understood. Now what to do? Our logic is simple. We calculate alpha and then only we go ahead. I repeat. While calculating hinge reaction, we calculate alpha, then only we go ahead. Okay. And we take a statement. My synopsis, you see that. In the synopsis, crystal clear given. For a given body, alpha, theta, and omega is constant about any axis. And or first statement in my rotational mechanics synopsis. First statement after heading, this one. So if I change the axis, torque may change. Anything can change. But alpha, theta, omega will not change. Do you understand? They won't change. That's the first and foremost thing you need to understand. So what I'll do is that I will change the axis to the center of mass right now. Once I change axis to center of mass, what happens? Tell me. Now tau is equal to I alpha. Again, we can use tau is what? Tell me. R1 into L by 2 is equal to I alpha. What is I? Right now, ml square by 12 alpha. So LL gets cancelled. 2 how many times? 6 times. Right? So we got R1 is equal to ml alpha. But how do we calculate alpha value? We already have it. Remember, torque will change, angular momentum will change, moment of inertia will change if we change axis. That's okay. But theta, omega, alpha will not change with axis. This is a very important statement you need to understand. So by using that statement, we go to apply this one here. Then R1 is equal to ml into 3g by 2l. What is the value? 1 minute. By 6, I missed it. By 6 is also there, na? Here, by 6 is there. That's a very common mistake for me. I'll cancel, I'll forget that. Because after cancellation, I write little below, na? While copying, I'll forget that. Always it happens. So, 3 how many times? 2 times. L gets cancelled. So, what is the value? Tell me. mg by 4. Is it clear? Good. So, that's good. What else? How can we handle this next one? R2. Anyone is there who can tell me how to deal with it? You reached a dead end there because torque will not give you R2 value. That's the problem. Okay. Torque will not give you R2 value. So what we say is that you can use force free body diagram, right? Check it. By going to the torque line, you reach a dead end, we can get only one answer. The other one, you are not able to get it. But see, the force line is good. So observe this. Rotation mechanics. When you are in trouble, sir, I'm in trouble, I'm not able to find one force. Just always think like this. Can I solve this by using force method? Okay, right. Clear. Force method. What is the force method? Tell me. F net external is equal to ma. Now concentrate here. What is A? Acceleration. Acceleration of what? Tell me. Anyone can tell me what is the acceleration of? Because previously we used to have a body, in a body, assume there is a block moving horizontally. We solved it in Newton's laws, right? When a block is moving horizontally like this, every particle will move with what? Same acceleration. So no problem at all. Acceleration of any particle you can take. But here it's not like that, na? In case of rotational mechanics, different particles are moving different acceleration. Now, what acceleration of what point you take? Tell me. If you say hinge, acceleration of hinge is 0, na? Yeah, tell me. Anyone? Acceleration of center of mass. Remember this. Right. It's very important to understand. In case of Newton's laws, you don't need to worry about it because every particle moving with what? Tell me. Same acceleration. So no issues. Rotation is the problem. So F net action is equal to ACM. It's a very important point. That's it. We solve. So what the F net action is equal to M. So let us go for that. Vertical direction summa solve panla. Sir, why we need to solve vertical direction? We already got R1. Na? Let us go through. And it confirms that method, whatever method you do, you get always right answer. Check it. Okay. We already calculated R1. Now we are going to calculate R1 once again. Observe net force mg minus R1 is equal to what? Tell me. M, acceleration of center of mass. Oh, I need acceleration of center of mass. How do I get it? Observe alpha is there. Right. When you have alpha, you can find acceleration of any point. I already discussed here. Check it. When you have a rod, it is having alpha. You can find acceleration of any point. When a disk is rotating, when it is rotating with alpha, any point acceleration you can find, right? So we need to find acceleration of what? Tell me, center of mass. So about this axis rotating, what is the acceleration center of mass? Tell me. Acceleration center of mass.
3g/4.
Come again.
3g/4.
3g/4. Yeah, correct. 3g/4. Perfect. You directly gave the answer. Okay. R alpha. Acceleration ACM is equal to R alpha. R is equal to L/2. What is alpha? 3g/L. Now what happens? 3g/2L. Sorry. 3g/2L. Now L gets cancelled. What is the ACM? 3g/4. Substitute the value here. So you will end up at mg minus R1 is equal to m into 3g/4. Now what to do? Swap them, right? So when you swap them, you will get like mg minus 3mg/4. What is the value? mg minus 3mg/4. Tarun, tell me.
mg/4.
mg/4, that is equal to R1, right? I got the R1 value by using force method. See, up to alpha, it's fine. Up to alpha in any method you have to deal with, right? Then I gone through the force, okay, mg/4, and torque method also I got the same answer. Now by using the same thing, I will check it. What about horizontal? Observe F net action is equal to ma. I use this in vertical direction. I got the answer. Now I'm going to use in horizontal direction. When I use F net action is equal to ma in horizontal direction, what is the horizontal direction force? Tell me. R2, right? Okay. R2 is equal to m into acceleration of center of mass along horizontal direction. What is the acceleration along center of mass horizontal direction? 0, right? 0, right? So A is equal to 0. Right. That implies what? Tell me. R2 equal to 0. You won't get complete clarity at this place. At this place, you won't get complete clarity. Sir, anak purila. Okay. What is my statement is, I will give the question, I will give a question to you. Okay. Solve it, then you will get the complete clarity. Let us call it as 5A. It's my addition to this one, right? You may feel, sir, you may feel, sir, I got it. No. Even if you feel I got it, just do it 1 minute. The rod is released from an angle of 60 with vertical. Understood? Now calculate hinge reaction. Exactly same question, no change at all. Only thing is I made it what? Tell me. 60 degrees with vertical. Okay? Right. So I'll make the final thing. 1 minute. 60 degrees, it is being released. Okay? So to avoid confusion, those who have clarity, very good. Those who to avoid confusion, after calculating alpha, don't go to the torque method. Go to completely Newton's laws method to get the final answer. Okay? Don't go here because this is dead end. Partially we are getting answer, complete answer varadilla. Okay? Right. So solve this, then only you'll get the clarity. Question number 5A. Solve. 5A. What is that? A rod is there. It is released at 6-degree angle. It is released at 6-degree angle. Calculate hinge reaction. This gives you complete clarity. Okay. Right. Let us go ahead with the question. Question number, the downward mg. Free body diagram we have to write. Then hinge reaction R1, R2. Let us write the force free body diagram also. The entire rod can be taken as a particle. Downward mg, R1, R2. This is the thing. Force free body diagram, torque free body diagram we have. Good. Then we need to use what? For the torque method and force method. Okay, we can do. First thing, observe carefully. Let us take the axis here. For entire problem, the previous segment you understood, whether you go through torque method or force method, the core is what? Alpha. Alpha is essential. So you have to calculate alpha and take the axis here. Go ahead with alpha. Tau is equal to, tau is mg L by 2. That's it. Check it. Is it only mg L by 2? No. Force into what, tell me? Perpendicular distance, right? So how do you get perpendicular distance? Extend the line of force and you have to take R perpendicular like this. This is R perpendicular, right? So this is R perpendicular. How do you get R perpendicular? L by 2. And this will be L by 2 sine 60. So L by 2 sine 60 will be L by 2 root 3 by 2. This is regarding how to calculate torque. We already discussed. Tau is equal to I alpha. I is ml square by 3 alpha. Perfect. Now m gets cancelled. LL square gets cancelled. So what is the alpha? Tarun, tell me alpha is equal to?
3 root 3
G by 4. Perfect. 3 root 3 G by 4. Let us remove this one. Yeah. Tell
So
me.
actually, moment of inertia of rod is ml square by 12. No.
1 minute. Right. 3 root 3 G by 4L. I missed L. 3 root 3 G by 4L. Good. This is alpha. Once you got alpha, then you can continue. Okay. Now, let us not get confused that two different methods. Only one method we go straight. We go to force method. After this, what we do? We calculate acceleration of center of mass, ACM. What is ACM? Anyone? What is ACM? Acceleration of center of mass. We know alpha. Once we know alpha, we can find acceleration of any point. If I ask you what is the acceleration of hinge? Hinge is at rest. Acceleration of this point, tell me. This point is at a distance of L. So acceleration is L into alpha. Now this is midpoint, na? Center of mass at the midpoint. So ACM is equal to R alpha. Understood? Clear. LL gets cancelled. So acceleration of center of mass is equal to 3 root 3 G by 8. Okay, we got a very good point here. After this, what to do? Now you may feel, sir, mg minus R1 is equal to MACM. No, because if you observe closely, I already discussed when you have a rod rotating with alpha, okay, acceleration of center of mass is RCM into alpha, fine. But acceleration will be perpendicular to what, tell me? That's a key point, na? I told you already, perpendicular to R. Check it, perpendicular to R. So if I write the acceleration here, I'll use green color for this acceleration so that some contrast will be there. Acceleration of center of mass will be like this. I don't want to, actually speaking, I don't want to write here because you may feel this is a new force. No, it's not a force. It's acceleration direction. Now tell me what direction acceleration is? Is it vertically downwards? No, na? So what I'm going to do is I'm going to take this acceleration, I'll bring it here. Now this acceleration will have two components, right? Tell me what are they? Vertical component and horizontal component. Understood? Now what is the vertical component? ACM cos 30 root 3 by 2. ACM sin 30. ACM by 2. Anyone is there, sir? How you conclude this angle 30? You want me to explain? If you ask, it is good actually. The reason is, observe that's not 30. This is just a minute. Just a minute. No, 30 or 60, there is a possibility now. Right. So how to deal with it? This is 60. Yeah, 30, correct. Perfect only. I did. Good. So 30, whatever I took is perfect. Now observe, net force in vertical direction is equal to acceleration in vertical direction. So I can write like this. In vertical direction, mg minus R1, is equal to m into ACM. What is ACM? This part. ACM is 3 root 3 by 8g into root 3 by 2. This is a vertical component of acceleration. Now, if you simplify, you will get the answer. So, mg minus r1 is equal to mg into 3 into root 3 into root 3 is 3. 3 3s are 9. 9 by 16. If you swap these two, direct step I write. Direct step I'm writing. mg minus 9 by 16. 9 by 16, how much? 9. 16. 7 by 16, right? Correct. So R1 is equal to mg into 7 by 16. Now what about R2? Same method. Net force is equal to mass into acceleration along horizontal direction. So net force along horizontal direction is only R2. R2 is equal to mass into acceleration along horizontal direction will be 3 root 3g by 8 into 1 by 2 because ACM. So R2 is equal to mg into 3 root 3 by 16. Question number 8 is identical to question number 7, 6, 7, or I can say question number 5A that I discussed. Some angle is involved, that's it, okay? So let us start. Now, there are two hinges are there. Two hinges are there, okay? 2 pins, I think so, hinged at as shown on the figure, and B is being removed, right? So for the better, for the understanding, what I'll do is that because B is removed, there is no discussion where must be the axis. Axis must be A. That's the first thing. And for the center of mass, location, all these things, I take the line that this is center of mass and I'll take this line. Center of mass must be on the diagonal, you know very well. So just for the sake of better understanding, it is on the line. Okay, now what happened? The pin B is removed. Pin B is removed. Okay, what to do? Standard stuff. Hinge reaction R1 and hinge reaction R2. Okay, then what? Gravitational force mg. Standard stuff, right? Okay, so tau is equal to I alpha. What is tau? mg into perpendicular distance. Extend the line of force. Extend the line of force. Okay, dotted line. And take the perpendicular distance, right? Take the perpendicular distance. This is R perpendicular, okay? So what is the perpendicular distance? L by 2, right? So no need to discuss. Directly I can write L by 2. Tau is equal to I alpha. Moment of inertia about center of mass will be, for rectangular plate, you need to remember from the table, M. A square plus B square will be there, but here L square plus B square by 12. Now, you want moment of inertia about this point, na? This is about center of mass. So, we need to take the parallel axis theorem. This length you need to calculate. What is that length? The diagonal by 2. Diagonal length is what? A square plus B square under root of the diagonal. Diagonal length by 2. That's a distance between these two. Now, parallel axis theorem if you use, torque about any axis is equal to, sorry, wrong statement. Moment of inertia about any axis is equal to moment of inertia about center of mass and mass into the distance between these two axes square, these two square, right? So formula you know, I is equal to ICM plus MD square. That formula I'm using, that is equal to M L square plus B square. I can take it common. If I take it common, it will be 1 by 12 plus 1 by 4, right? This square, check it. Then you will end up at what? Easy. M L square plus B square by 3. Understood? ML square plus B square by 3. That's a moment of inertia. So ML square plus b square by 3 into alpha. So you got the alpha value. Alpha is equal to 3mgl by 2 into L square plus B square. We got the alpha, right? Good. After getting alpha, what to do? Calculate acceleration of center of mass. Let us remove these two because unnecessary. No more required. Okay. Now calculate acceleration center of mass. ACM is equal to R alpha, right? ACM is equal to R alpha. What is R? What is R? Tell me. A square plus B square under root by 2. What is alpha? This is alpha. Sir, we can cancel this. Yes, we can cancel this and this. Don't do that. Keep it as it is for time being. Okay. If you want, you can simplify this one. Like this is 4. This ACM. But observe carefully. ACM will be perpendicular to R. This is R. This is the perpendicular, right? So ACM will be perpendicular to R. ACM, right? Oh, now there is a problem there. This angle is theta, right? If this is theta, this is 90 minus theta. This will be again theta. Okay, good. Theta. Now, what to do? Vertical, if you want to take. Okay, let us call it as AY. AY is equal to ACM cos theta. And AX is equal to ACM sin theta. Up to this is clear. Now, it's a matter of simple calculation. What is cos theta? Observe, you have this triangle with you, and this is angle theta, right or wrong? This is angle theta. So what is cos theta? Adjacent side of hypotenuse. So it can write it as ACM into adjacent side is L by hypotenuse is what? Tell me. L square plus B square under root. B square under root.
So
And
in the alpha, M1 comes, sir.
yeah, M won't come. M is not there. Correct. You're right. M cancellation I haven't done, right? M gets cancelled. You're right. So here also M won't come. Good. Let us continue. ACM is equal to B by square root of L square plus B square. Now you have to put the value of this ACM in this to find AX and AY. Let us calculate first AY, then we go for AX. So final value of AY is equal to, if I put this value, direct step I write, if I put this value here, right? This A square plus B square under root, B I wrote, L, L square plus B square and L square plus B square under root, these two gets cancelled. Na? So you will end up at 3G L square by 4 into L square plus B square. You will get this one. This is AY. Similarly, AX, if you take it, AX, it will be 3GL B by 4 into L square plus B square. Understood? We got AX and AY. Once you got AX and AY, then job done. The easiest one will solve. Along horizontal direction. Okay, I haven't written force free body diagram. Na? What's there in it? Because of enough practice, what I do is that from torque itself, I can pick up the force. I stop looking into the perpendicular distances. Okay, vertical force is R1 mg directly I'll do. But you may be a little confused. You may get a little confused. That's why I'm writing it. It's okay. So along horizontal direction, R2 must be equal to what? Tell me. R2 is equal to M into acceleration along horizontal direction. 3GLB by 4 into L square plus B square. That's done, easy. Then what about vertical direction? Net force is equal to mass into acceleration, right? So mg minus r1, mg minus r1 is equal to m into ay, 3gl square by 4 into L square plus B square. After this, purely mathematics. Can you calculate? Yes. What to do? This R1, bring it here. This entire value, take it there. So that implies R1 is equal to mg, I'll take common, mg 1 minus 3L square by 4L square plus 4B square. Okay, let us not do that. 4 into L square plus B square, right? If you simplify this, you will get that, 4L square minus 3L square is L square. So mg into L square plus 4B square by 4L square plus B square. Yeah, perfect. This is the answer. See the line, how we gone through. Okay, right. So what we are doing here, to find hinge reaction when there is alpha, we used axis at the hinge and we found alpha. From alpha, we found ACM. Once we got ACM, we resolved into mutually perpendicular. Net force is equal to acceleration along y-axis. Net force is equal to mass into acceleration along x-axis. Sir, can't we take these two axes? 100% we can take. Then I recommend to take the hinge reaction like this. Both ways, you will get the same resultant hinge reaction. That's all for today. Thank you.